Hello everyone, I'm Iris Yazıcı and today I'm going to present my EE102 project. The purpose of my project is to estimate the key of a music piece by finding the most played notes throughout the music piece. My project has two parts. The first part is displaying which notes are being played on the LEDs, and the second part is finding the most played notes. Let's start by testing the first part. Each note is displayed on different LEDs, starting from C, C sharp, D, D sharp, E, F, F sharp, G, G sharp, A sharp, and B. Let's give an 880 Hz sine wave. We can see the output here, and as we expected, it shows the note A correctly. Now let's try 1046 Hz. We are expecting to see the first LED on, so I play, and the first LED is turned on. Now let's try playing a piece from Chopin. Here on the LEDs we can see the notes changing. Now we are going to try finding the most played note. As a start, we are giving 880 Hz, as you can hear. Let's program the device to start. Now we are seeing the 880 Hz. Now I'm switching to 1046 Hz. And as you can see, after waiting some time, the output also switched. Now let's switch to another frequency. And as you can see, the LED also switched after waiting some time. The LED follows the most played note. Finally, I will play a piece from Chopin and try to estimate the key of that piece. Let's program the device. And let's start the music. Okay, now we can see the outputs. The LED shows the most played note up until that time in the music. We should wait a bit for the LED output to settle down. And to see the correct output, we should actually wait till the end of the piece. Now it's showing C. Now it's showing D sharp. And actually, D sharp is the correct key. Yeah, so now it's found the correct key. But the piece isn't over yet, so the LED might still change a bit, but in the end it will settle down to D sharp. Now let's quickly go over the setup. The sound is taken from the speaker output of the computer with a jack-to-jack cable. This cable goes into a jack input, which has a positive and a ground pin. This is 0.2 volts RMS. We have this circuit on the breadboard, which makes the voltage squeezed between 0 and 1 volts, an appropriate voltage for the basis 3 pins. Also, we need to give 0.7 volts for the breadboard circuit from the power supply. Here you can see the schematic of the breadboard circuit. The approximate output voltage is given here. That voltage is given as an input to the XADC of the basis tree. Though the XADC is in the left bottom part of the board, the parts that you can see we are using are extensions to the XADC ports. So the analog sound signal coming in is converted to digital by the XADC in the basis tree. After that, the output of the ADC is given to the FFT IP. By analyzing the output of the FFT, frequency and corresponding magnitude of the complex output is calculated, which are then used to find the most played note. Also, the button is the reset input for the XADC, and we should press the button once for the code to start working. Now let's trace the code together a bit. We have the clock input, which is the 100 MHz internal clock of the basis tree, and this clock is provided to both the XADC wizard and the FFT IP. We have the switch input, which is the active low reset for the ADC, and 2 bits of the JA input, JA4 and JA0, represent the positive and ground terminal of our incoming analog sound signal. Other bits of the JA are not used, and the most significant 12 bits of the LED are used to display different notes. Then we have in the architecture the XADC wizard's component declaration and the standard ports it has, plus the ports which come from using the XI4 stream. Then we have the component declaration of the FFT IP. As you can see, MX's data T data is its main output that we are going to use, and it has 32 bits, and the 16 most significant bits are the imaginary part, and the other part is the real part. And then we have another component, which is a simple code which calculates the magnitude, like the magnitude squared. It squares the real parts plus it squares the imaginary parts and gives the output magnitude. Okay, so we also have the port maps for the XADC and the FFT IP. The output of the ADC is called MX's T data, and it's connected to a signal called payload. The 12 most significant bits of the payload is used, and we concatenate zeros to its beginning and give that as an input to the FFT. Now let's see the port map of the FFT. As you can see from these port maps, a transfer from the ADC to the FFT only takes place when the ADC is ready to give data, so its T-valid output is 1, and when the ADC has finished its calculations, so when the FFT is ready to accept data. Here is a process that says if we are on the rising edge of the clock, and if FFT is ready to provide valid data, and if magnitude is above a certain determined threshold, which could also be 0, then frequency is calculated as with this formula. The sampling frequency of the XADC IP is 40 kHz, and the FFT sample size is 2 to the 14 data points. We can calculate resolution by dividing the sample frequency by the FFT sample size. So 40 kHz over 2 to the 14 gives us 2.44 Hz. If we multiply the resolution, which is the delta F, by the T user, the XK index, then we can find which frequency a particular FFT output corresponds to. T user is an output that the FFT IP provides us with. In the comments, you can see 5 different frequencies for each of the 12 notes. So there are in total 60 frequencies which can be detected. When a particular note is detected, we add the magnitude of the current FFT output to the existing total amplitude of that note. Finally, we form an array with 12 elements, each element being the amplitude of a particular note. The index of the most played note is found in the following for loop, And we use that index to determine which LED should turn on.